In this lesson we deal with a theoretical interesting problem that has a considerable practical involvement. It is the theme of elementary transformations of matrices. Our objective will actually be to demonstrate the formula of the determinant of a matrix, and then we will complement something else because it is a subject that has other applications, being a good time for adding this small contribution. Let's start talking about some transformations, which we are going to call elementary, because they are very simple, and the idea is as follows. Let's define first of all what we mean by type 1 matrix, which you have defined in the transparency. A matrix is type 1, when in the identity matrix, we just change one of the ones on the main diagonal, by the Q value, which has to be different from 0. So, there you have a case, which is the matrix Q1, where the third element of the main diagonal, have been changed it, so, it is a type 1 matrix. Now let's consider a general matrix A, which has the elements that you see there, and we're going to post-multiply this matrix, by the type 1 matrix, Q1, that is, we multiply the matrix A from behind, by Q1, and we get the matrix that you have there. It is interesting that, as students, you do it by hand, so taught you can see that effectively the result is that matrix, and in addition, you refresh the product of matrices. So, we observe that if we multiply, from behind, a matrix, by a type 1 matrix, what happens is that one of the columns becomes multiplied by the value that we have changed in the identity matrix, and the other columns remain identical. Which column is the one that is multiplied? Since we changed the third diagonal element of the identity matrix, it will be the third one. If it were the second, it would be the second, and if it were the first, it would be the first column. So, a way to multiply a column of a matrix by a factor, is to post-multiply this matrix by a type 1 matrix. To finish this, we will say that the determinant of this matrix is Q, that is, it is the value that we have changed in the unit matrix. Let's move on to type 2 matrices. In type 2 matrices, what is done is, instead of changing a 1 of the identity matrix, a 0 is changed. So, there you have an example, matrix Q2, in which the element in row 2 column 3, which was a 0, has been replaced by the value s. What happens if a matrix, a general one as before, is post-multiplied, that is, from behind, by a matrix of this type 2? Well, we do the product, and I invite you to do it by hand, and what do we observe? Here we see that two columns remain exactly the same, but the third column is equal to the previous third plus s multiplied by the second column. So, it can be seen that if we want to multiply a column for a value s, and add it to another column, and put it in the ladder, of the columns from this matrix, we have to use these type 2 matrices. It is interesting to know, that if the element that we change in the identity matrix is in row I column j, what happens is that to column j the column I is added multiplied by s. Then it is important that we see where to place this element s, so that it produce what we want, that is to say, that one of the columns becomes herself plus another column multiplied by the value s. Finally, we have type 3 matrices. In the type 3 matrix, what we do is exchange, in the unit matrix, a row by another, or a column by another. It is the same, due to the symmetry of the identity matrix in the case of the matrix Q3, that you have in the example. What we have exchanged has been either the columns 2 and 3, or the rows 2 and 3, it does not make a difference. So, the question we ask ourselves is, what happens if we multiply a matrix by behind, by a type 3 matrix? If you do it, you will see that what happens is that the two columns are exchanged, those corresponding to those we have exchanged in the unit matrix. The matrix that it turns out has the first column unchanged, and columns 2 and 3 have been exchanged. The determinant of this matrix is -1. We are going to apply these ideas from the elementary matrices to the case of the orthogonalization algorithm. We are going to consider a matrix. We'll see later why is this matrix. This matrix T is an identity matrix, in which the last row vector is replaced by the vector, minus T1 divided by Q, minus T2 divided by Q, and 1 divided by Q. Now we are going to multiply any matrix, in this case of dimension 3 by 3, from behind, by this matrix, and let's see what happens. If we multiply, what we find is the shown matrix. The third column is the previous one divided by Q, which is just what we did in the algorithm with the pivot column, which we divided by its pivot, that is, Q, and then, the other two columns are the same columns minus T1 or T2, which are the scalar products of the corresponding columns, by the transformed pivots columns, because a sub 1 3, divided by Q, it's just what appears in the third column, and the a sub 2 3 divided by Q, also and the a sub 3 3 divided for Q. So, we see that if we have in the algorithm a matrix, and we want to calculate the transformed matrix, precisely what we do, is what we are doing here, then, it is equivalent to proceed as we did in the algorithm before, and to multiply, by behind, by a matrix of this type. The only thing that needs to be done is that the values, T1 and T2, have to be the scalar products of the corresponding columns, and the value of Q, has to be the pivot value. So, we are going to demonstrate that this matrix, that we have used, the matrix that we have obtained when transforming, you can get it in two forms, either multiplying from behind by the column of the matrix that we have indicated, or we can do it, in 3 steps. That final matrix, which appears there, can be obtained as a product of 3, one of type I, in which one diagonal element of the identity matrix is divided by Q, one of the ones, another type 2 matrix, in which we have seen that one of the zeros can be changed for a value, T1 divided by Q, and another matrix, also of type 2, where another of the zeros is changed value, which in this case is minus T2 divided by Q. If you multiply those 3 matrices that appear there, precisely what you would get is the matrix that includes that product. Then, it can be done, step by step, as done in the algorithm, or the final matrix can be obtained directly. Remember that first, we change only the pivot column, and then each of the other columns, and each matrix corresponds to one of these processes. Now let's see something very interesting. I refer to the formula of the determinant. When we explained the orthogonalization algorithm, what we were doing was to give a formula for the determinant, that seemed to fall from heaven, and that we had not proved. Now, let's show that that's the way it is. Let's remember that in the orthogonalization algorithm, we normally start with the identity matrix, but we can start, as we already know, from any regular matrix, that is, any matrix whose determinant is different from 0. Let's assume that we start with regular matrix B. Next, we enter vectors, we pivot, we enter vectors, we pivoting, and we have seen that this operations of pivoting can be done step by step, first transforming the pivot, and then each of the other non-pivot columns, or it can be done, by multiplying by a matrix T, of these that we have just seen. So, if we start from the matrix B, multiply by T1, in the first vector that we enter the second vector, we multiply by T2, and with the last vector, we multiply by Tn, what we get is the final matrix, which results at the end of our pivoting processes, but we know that this matrix does not have to be the inverse of the matrix, built with the vectors that we have been entering, because they may be in the wrong order. How do you change the order of columns? With the type 3 transformation, then if we apply as many transformations P1, P2 and Pp, as required, to place the columns in their place, we know that the result is the inverse of the matrix A. Therefore, that equation that you have there, the inverse of A equal to B times T1, by T2, by Tn, by P1, by P2, by P sub P, corresponds precisely to the pivoting algorithm. We start from the matrix B, matrices T are the transformations that we are using for pivoting, and matrices P, which are the transformations that we have to use to place the columns in their places. But the final result is the inverse matrix of A. If we now take determinants from that matrix, as it is a product of matrices, which are all regular, it turns out that the determinant of the first matrix, which is the inverse of A, is the product of the determinants of all factors. However, we know that the type I transformations had as determinant Q, the type 2 had determinant 1, and those of type 3, determinant -1, and that's what we apply next. Then, we have determinant of B on the one hand, determinant of T1, which is 1 divided by its pivot, determinant of T2, which is 1 divided by its pivot, determinant Tn, which is 1 divided by its pivot, because it was divided, not multiplied, by the pivots. Then, it is the product from 1 to n of the inverses of the pivots. They are 1 divided by the pivot, because we divide by the pivot, we do not multiply by the pivot, then that product appears from 1 to n, of 1 divided by q sub I, and then, the P matrices, that we know they have determinant -1, then, it's -1, times -1, times -1, as many times as the number of matrices there are. If they are P matrices, we get -1 raised to P. Then, we have the determinant of the inverse of A, is equal to the determinant of B times the product of the inverses of the pivots, times -1 raised to P. From there, taking into account that the determinant of the inverse of A is 1 divided by the determinant of A, simply clearing, we get the formula of the determinant of A, which is not another thing that, -1 raised to P, the number of times you have to change the column matrices, so that they are in order, the determinant of the inverse matrix of the departure, that if it is the identity matrix, is 1, and is raised to -1, that is to say, which is the inverse of that of A, and then by the product of the pivots. In this way it is proven that FTHE formula that we have used was correct, and that is a formula, which is derived from the algorithm of pivoting, and from the theory we've seen of these elementary matrices. Finally, we'll see what happens if these elemental matrices, instead of being used to post-multiply a matrix, they are used to pre-multiply, that is, they multiply placing them ahead. If we used a type I matrix, we multiply it ahead of any matrix A, what we get, as can be seen, is that the row, in this case row 3, is multiplied by Q. So, the type I matrix serves to multiply one of the rows of a matrix for a given value. In the case of type 2 matrices, if we use them to premultiply another matrix, what do I get? Well, as you can see, all the rows are exactly the same, but one, which is itself plus the value s by another of the rows. Finally, in the type 3 matrix, if we use it to premultiply, what it is going to happen is that two of the rows will be exchanged, while if we do it from behind, we exchange two columns. With all this, it is clear that the use of elemental matrices in these elementary transformations allow us first, operate very well with rows and columns, because we can exchange them, we can multiply them by factors, and we can get combinations of some columns or some rows with others, and finally, it serves us also to demonstrate the formula of the determinant of the matrix.